Benji and I, we met at our previous employers, and we still talk, every couple weeks to this day. But he's an avid diver, and he's got some really cool projects like that with diving coming up, and in addition, he's a Go developer. This is one of his talks he presented at GopherCon, and I said it'd be perfect for KernelCon. And please put your hands together for Benji Vesterby.
All right, everybody hear me? Cool. So I'm going to be talking about secure coding in Go today, specifically Go because it's what I work in most of the time, but everything that we're going to be talking about here is actually applicable across any language and communication system. This is my overly verbose title, which is awesome when you try to put it on YouTube because it cuts off the last like 3 words. So the first thing we're going to talk about is developing a secure mindset and habits, and how the knowledge of how applications are compromised actually allows you to better identify those issues during code review or development, things like that. Talk about going through the actual, like what a code review looks like, and then different ways to ensure that your software development lifecycle is secure for your teams. Through the use of automated testing or fuzz testing, and we'll cover a few of those different things. The first rule of AppSec, though, is don't trust user input. And just the second rule, so that everybody else knows, don't trust user input. So what is user input? We're going to specifically be talking about mostly HTTP APIs. This is still applicable to like gRPC, protobuf, GraphQL, all of those different things. It applies to databases and all that stuff, but we're going to be specifically covering HTTP because I have a demo app that's written in HTTP. Who all here is familiar with Go as a language? A few of you. So Go is a programming language that is statically compiled onto a system, creates a single binary that can be run on, or based on the architecture of your computer, and it's a general purpose language similar to Python or .NET or Java. Its use is becoming much more wide, and the language was developed back in I think they announced it in 2009, and then the first version was released in 2012. And so there's a vulnerable application if you want to check it out. The link here is my blog where I actually link to the slides as well as the code and a bunch of that additional information. I'm also working on a blog series to go with this that goes into each individual vulnerability in much more detail. But we're going to be playing with an app today that allows you to create a user account, upload and display photos, store user information in a database, and then search that database for photos. And we're going to walk through different steps for actually compromising that application, and really dig into why something might be a vulnerability that doesn't look like it's actually a vulnerability. The first thing we're going to talk about is injections. I think it's still the #1 on OWASP, but the vast majority of vulnerabilities that you see fall into this category of injection. That's HTTP header injection, SQL injection, cross-site scripting. I think they lumped in cross-site request forgeries and lots of that other stuff. But we're going to be focusing, for the demo, we're going to do a lot of injection. And here's a non-comprehensive list of the available injections. We're going to be covering primarily the stuff at the top there, although the demo app is actually vulnerable to both reflected and stored XSS, but I didn't add any unsafe redirects. So the first thing we're going to talk about here is, let me swap over to the code. Can everybody see this? Oh, that's a little small. Hold on one sec. Is it better? All right. So one of the first things is, and this is not exactly a vulnerability, but it's one of the first things that attackers are looking for when they attempt to compromise an application, is for ways to get information out of the application without giving away their presence. One of the ways they do that, though, is looking for iterable data. And this application is written using integer-based user IDs, which are iterable and can just be queried in a loop with like a curl statement. And I will show you what something like that looks like. So here you can see a curl statement executing a get call against the API. And what it's doing here is it's looping for from 1 to 10 and passing that user ID in and then just JQing the result. And then also attempting to find all images associated with the same user IDs. And we'll go ahead and iterate through this here. Oh, helps if I actually start up the... Sorry, 1 second here. All right, so now we should actually have data. All right, so what we can see here is if we go back up, you can start seeing that the individual users are broken out. It contains some information about each user and their ID, and then password, which is empty in this example, but we're gonna talk about why that's important at a later point. And then each of the individual images associated with that user. And we were able to find this because we could open up a web browser if there was a UI and look at the actual network calls and say, hey, we've got a user ID that's an integer, it's being passed into an API endpoint, and then we can make some assumptions based off of that and do some testing to iterate over those users. So the way to actually protect against this is to use something like a universally unique identifier. If you're using Go, this is the one that I recommend. The community is primarily switched over to this, but it's theoretically impossible, well, not impossible, but the statistics are it's very, very highly unlikely to have a collision in the ID that's generated from this system just because of the actual scope of the algorithm. And so that's the fix for that one. It's like I said, it's not really a vulnerability per se, but it does expose information about your application that an attacker can use to then actually exploit the application. And that's what we're going to be doing. So we're going to go through a number of different injections here. The first one is I want to go ahead and query user. So what I'm going to do here is I'm going to just query user 10. And this is my user, and I am a bad gopher. And I want to get some information about user 1, which we've already iterated through the IDs, but I'm going to go ahead and do it again here anyways. And so I know now that user 1 is Gopher Prime. I've got its email address, and that's it for now. But if I want to try and get all of the users through this same system, what I can do is I can actually encode the data using URL encoding, which I actually have an example of here. So it takes the query on the left here, because I'm using a SQLite database under the hood, and it's purposely vulnerable for SQL injection. I'm taking the or 1 equals 1 on the left and converting it into a URL encoded version on the right, which is then being injected into my SQL database, and you can see that here. And when I do this in the user ID field, I actually get nothing because I probably didn't do my changes. Give me 1 second. All right. Let's try that again. And it didn't work. Awesome. All right, let's fix it on live here. So we're going to make this vulnerable because I might have accidentally committed my code changes, which is great. So we're going to go into the get user, and interesting. Well, I'm not sure why that's not working. So let's a get call, user ID. So looking at the query here, it should actually be an injection because of this printf the funked printf statement here. Generally, what you're looking for when you're looking for a SQL injection is using string interpolation outside of the database driver to actually like put the value in the string here. Oh, I'm actually using a limit 1 on this. That is probably what I changed. Let's see here. Yep. Well, we can go ahead and just move on though. But I can actually I'll just walk through the code a little bit here. So what's happening here is that we're defining a SQL statement literal in the actual code, and then we're using this funked sprintf function here to add the ID for the user. When you're doing that, you're bypassing the protections of the standard library or whatever your database driver is underneath. And what that causes is that string is just inserted literally into it as a value. In Go, this is a really easy thing to fix, and even though I can't actually show the vulnerability for some reason. All you have to do is take that sprintf off, and then change this to a question mark like this. And that will actually, that'll fix the issue there. And obviously it should only show the one. Oh, wait, no, it did, my bad. It did work. It did work. The injection did work. Okay. I forgot that it doesn't show all the users. What's happening here is I'm bypassing the ID check. And because I'm bypassing the ID check, it's actually giving me the information of user prime, which we actually already knew from our other part. But if you, so because I'm not actually passing an ID. And so when I do this curl call, when I do the curl call again, we'll do it again here. So I'm getting user 1. But we didn't actually pass the user ID into the query string. We passed in the injection, right? And so it actually returned user data that we should not actually be able to see from this. And then to fix it, that's my bad. I thought it was going to give me the full list. That's a different part. And so to fix this, we just change this to a question mark. We remove the sprintf call, like that. And then we go over here and rerun it. And then try the exploit again. And get nothing. All right. Sorry, that was my bad. And what you can see here is that because we're using the SQL driver for that, for SQLite under the hood, and we're not interpolating that string manually using the sprintf function, we are allowing the driver to say this is unsafe and correctly encode the actual value so that it doesn't cause a SQL injection. It's actually, ironically, one of the most common vulnerabilities that you can see, and I found it a few times in Go and written a number of them myself. All right, so we went through the user query injection fix. We're going to talk about friend injections because I like friends. Everybody likes friends, right? And my user has no friends, which is what the null here shows. And it's still really small. Are you guys able to see that in the back? Okay, all right. So I want to go ahead and have friends. And how I'm going to do that is I'm going to check and see how many friends user 1 has. Because, being the first user, they probably have a lot. They only have 2. But, I want to have those friends as well. And so what I'm going to do is I'm actually going to get all of the friends. So I'm going to pass the same injection that I used before into the friends to give myself all the friends because I like being popular and that's what I want. So Now we can see that I have all the friends, and I am the best gopher. Although, ironically, I didn't actually get user 1 in here. And so I got a full list. Now, this is actually a really interesting query here. And there's a couple of different problems. Does anybody notice the difference between this list of users and the one we saw before? Passwords. Yeah, so this is actually an example of another type of, it's not a vulnerability per se, but it's actually a form of data over, like over returning data. So this is actually inside the code here. There is a query that says get friends. And unlike some of the other queries, I'm actually using what's called a struct scan. And how this works is it'll actually allow you to query based on the type of data that you're passing in. So I'm calling into the database driver and passing this struct to it. And I'm using a select star on my database. So I'm saying, give me all my columns and map it to my struct with the fields that are there. And because I'm doing it this way, instead of asking for very specific fields of the user, what's happening is the driver itself is binding that password that it returned from the database to that structure and then returning it out through the API. So this is actually fairly common to see where engineers kind of like take shortcuts to simplify their database interactions, where they'll define that type and then have a library that just says everything on this type should be in this data, so combine them together. But it can lead to issues where you can like overexpose sensitive data, and this is a good example of that. And this data specifically is gives you the password, and I don't think I actually ended up putting roles in the database, but if they had roles, you'd be able to see those and identify, who's an admin or who's a user or moderator or whatever. Interestingly, on this. This actually can also be used to help us identify what kind of password hashing mechanism is being used for their passwords here. And I think we're using I ended up using SHA-1 in this database, which we'll get into that a little bit later. All right, so we talked about friend injection. So so far, like assuming that you're using a sufficiently safe cryptographic hash, the exposure of the password here could be, while it's important to not have that, it could be something where it's not necessarily going to immediately cause somebody to be able to exploit your application. But the fact that there's SQL injection lets the attacker know that there are likely other ways for them to actually attack it. And we're going to go ahead and do that. We're going to probe for a let's see here. So we probed for users. We're going to go ahead and attempt to let's see, what did I have this one for? Yeah, okay. We're going to go ahead and go to oh, real quick. So while I was building this out, I actually denial of service my laptop. By finding a vulnerability in the driver that I was using. Anybody want to see me tank my laptop? Yeah? All right. So what I found is that, so there's this union select statement, which I actually just executed. And you can see that it works. And I forget exactly why I was doing this. Probably because I wanted to be able to determine whether or not I could union off of a separate table and accidentally expose more data. But while I was doing that, I incorrectly created the actual query for this and added an extra semicolon at the end, or I added a semicolon. You can see it here in the comment. And what ended up happening is it locks up the driver. So I'm going to execute this, and you'll notice that nothing is happening, right? Like it's just sitting there attempting to query the system. So what I'm going to show you is that you can actually see my memory starts spiking up here in a second. So we're at like 3.41 gigs of memory. Let's see if I can pull up that specific process. Yeah, it's really small. It doesn't look super impressive at the moment, but it is actually spiking it up. But what's actually, yeah, so you can see, can I actually zoom in on this one? So you can see that it's starting to spike up here. and the longer it goes, the more memory it's just going to use. Like it's a non-stopping thing. But more interestingly is that, let's say, for example, I'm trying to denial of service somebody's API. This specific vulnerability doesn't stop when I cancel the HTTP request. So I can go ahead and cancel this. My curl is no longer running, but the actual memory utilization will still continue to go up. Like right now we're at 15.54 gigs. There's 16.3 gigs. It's just swapping it into the drive, which is why we're not seeing it. So I don't actually know exactly what the driver has done wrong here, but what I suspect it is that it's a recursive query because of the union select. So what's happening is, and this is speculation on my part, is that it's recursively unioning the same tables over and over again, attempting to create a giant table of data to return back, but it's an unending recursive call. Like we're up to 24 gigs. So it's most likely the union, but the semicolon is probably what's triggering it to actually happen. I'm not 100% sure. This was like an accidental thing while I was building it. So I have to actually go and kill this process. Because otherwise, also if I use script. There we go. It is 68.98. All right, and we should see it go back down. No, it's a problem with the driver itself. So what happens with Go when you're talking about something like SQL is the actual, I'll show you here. So this database, the SQL package in Go is actually just a sequence of, let me see if I can actually pull it up in the first tab here. How it works under the in the background is that the SQL driver is actually an implementation of a standard interface in Go. And so the SQL driver package itself defines a series of, this is the interface that you have to implement for your driver to work in our standard library. And then there's actually an init function. Let me see if I can pull up the user page here, because I'm using a standard library call in this one. Connect. Let's see if it's in main. Okay. Yeah, so this underscore here, what this is doing is it's importing the package into the main function. And the reason it's an underscore import is because I'm not using the SQLite driver in my code. And so what happens is when you put the underscore in there, the init functions for the actual driver execute inside of that package, and they register themselves into the SQL driver. And then when you go down and actually, because if I go to SQLite next, let me find out where this is at. Helps if I don't have my, let me remove that. It's a massive file. All right, so db.go. Okay, so if I go to db.go, you'll see it. So here it is, SQLite 3. It's initializing the database. What's interesting about this is that this SQL right here is actually the database SQL package. But what's happening is when you call open on it, you're passing the key that identifies your driver. So if we actually pull up the code for that SQLite package, we can actually see the init function in there. Let's see here. So if we go in here, we should be able to actually find his init function. There you go. So here is the actual init of this driver into the SQL database. So it calls the SQL database package and actually calls register on it, passing its key identifier, and then like an instance of the SQL driver. And because the SQL driver implements the interfaces of the SQL, like the database SQL driver, it can actually run as that, and that key value is what's creating that relationship. So you can actually like load up a bunch of different drivers in Go, and then open individual ones passing a different key. So I could have one for MySQL or Microsoft SQL Server or Postgres, all loaded into the same binary, and then I just pass the right key for the one I want to use, and then it's good. That's how that works. Yeah. Yeah, okay, so when you're doing code reviews, what you should be looking for is the, anywhere where you see a, let me go back to the friends. sprintf is primarily what you want to look for. So if you're seeing something like this, so this is actually an example, and why this is included is because for the majority of cases, most engineers are not building their own data access layer, so they're not building the code that's sitting on top of the database. And what they're doing is they're interfacing with code that another engineer wrote that gave them an API that's easier to use. The problem with that in Go is that it automatically encourages people to use something like string interpolation rather than actually using the driver. So this is a prime example of that. I have abstracted the actual query call into this function that's a generic. And inside of here, all I'm doing is opening the database, executing the call. But the user is having to pass the full query to me, which is encouraging them to use sprintf, and then that is string interpolation bypassing the protections of the driver. So if you're doing a code review and you're talking about Go specifically, and actually this is pretty much any language, Python, Node, all of them. If you see somebody using string manipulation functions to add string data into a query, that is a pretty clear sign of SQL injection. And like there's lots of ways to bypass that, even if somebody is like tries to clean it ahead of time. And like different forms of like encodings and stuff like that to bypass the actual like where people will create custom validators to identify like, hey, is this a SQL injection attack? And then an attacker can just encode it a different way that bypasses that custom detection. So like here, like my recommendation is to lean on the people that created the database driver to properly handle like making that data safe. Yeah. 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 Well, the driver itself was the only thing that I saw the vulnerability was for that denial of service, and that was accidental on my part. I don't know what caused that, but the driver itself is still correctly handling the string interpolation, which is what that first example was, where I modified the user and took out the sprintf and added the question mark. That was actually me correcting the code so that the driver handled that injection of the data. Yeah. Yeah, well, yeah, yep. There. Let's see where we at. Okay. So I'm gonna go through grab mine. So we're gonna do a couple more examples. We're gonna do a login bypass with SQL injection, which is just kind of fun. And so what we're going to do is we are going to attempt to log in as the Golang Gopher, which is, I believe, user 1. Oops, I actually start my server up. All right, so we're logged in as Gopher Prime. And the password for Gopher Prime is Hello Kitty Club 2022. Which I created this in 2022, not 2023, so it's bad on me for not updating the year in my password, right? But you can see that it correctly authenticates Gopher Prime. So it's taking in that password, it's doing its hashing, and it's verifying does this password match. All right. So the next step is what we're going to do is we're going to attempt to bypass the hash check by injecting into the query here I think I'm doing a header injection here. Let me see. Okay. Let's see, bad password. Okay. This is just to show that the actual password fails. So we've passed in a bad password. We get a correct status code. It couldn't verify the hash. All right. So now we're going to try to bypass it by adding a single quote double dash to essentially, if we go into the login and log in the user, we'll look at the actual query down here. All right. So this is manufactured for this example, but it does actually happen this way. What we're seeing here is we're adding in this dash, or the single quote double dash into the actual command here after the email address. And what this is doing in the code is it's adding that at the end of email here and commenting out everything past it. So the query becomes select all from users where email equals gopher, whatever the gopher prime email is, and then it limits it to 1 and essentially validates that the user is who they say they are. Now, this is a manufactured example because the fact that both where clauses are on the same line here is what's allowing this to work, but it doesn't mean that this is not you will actually see this in your code, or not your code necessarily, but other people's code regularly. And so we're going to go ahead and bypass it by passing in the injection, and now we're authenticated as Gopher Prime. No password, just all it was a single quote double dash. Any questions about that? Yes. That's a problem with the developer that wrote that. Yeah. So you would, for this one I'm using, let's see, a struct scan. So I would actually do, let's see here, query row scan. There's my query. There it is. Okay. So how I would do this is I would actually just take this out and put it in here. This. Sorry, that was incorrect. It's actually this whole statement here. So that's what we're going to do is parameterize it, but you have to do it on the driver itself. So we're going to take the query that was here, we're going to paste that in, and then we're going to replace this with a question mark, and then get rid of this. And then that should actually correct the issue, assuming that it builds. Hey, there we go. All right. And then we will go ahead and query it with doesn't matter, and you get a failure. So it's using the driver to correctly manage that string interpolation, right? Rather than using the sprintf. Like you'd be surprised how many times you see somebody using string interpolation that's using an sprintf and not actually using the driver to pass data in. Like there's a reason that it's one of the most common in Go even. And so it's literally just pass it into the database driver directly, and that's where that problem comes into. You have a user that's responsible for creating your data access layer, and then you have a person that's responsible for using that data access layer. And the vulnerability can occur at both of those places. And if somebody does string interpolation above your data access layer, even if your data access layer is correct, they're creating a vulnerability there that then gets passed in down the line. Let's talk about unsafe file upload and path traversals. So path traversals in and of themselves aren't a vulnerability per se, but they can be used to exploit additional vulnerabilities, similar to like iterable user IDs. So detection of a path traversal is something that we're going to do here. And we're going to say, all right, we're going to list the images for a user. So here's user one's images, and we saw this in the original iteration script. And then what we're going to do is we're going to pass in, because this is, so we're going to use a header injection and attempt a path traversal to see what is above the user, that directory where that user's images are listed. And so you can actually see that all of the code, this is actually all of the code for this demo app, is in a directory above. And so that lets us know that we can actually move around the file system by passing path change, path modifications into this user header. And so what we're going to do is we're going to see if we can actually access a more sensitive part of my laptop. We're going to attempt to see if we can access the SSH directory to grant ourselves remote access. So there you go. You can see I have some Google Compute keys, a GitHub ID file, some known host stuff. So we know that we can access outside of the actual root directory of the API. And then the next step is, let's see if we can upload a file. So the system comes with the ability to upload images of yourself. And so we're going to go ahead and upload an image of Go For Me, which is actually, I should have changed this by now, but there's actually a problem with this where it overwrites an existing file. But this is showing that there's a file upload essentially, right? And that the file was able to be uploaded to the directory. And then what I'm going to do is I'm going to attempt to probe the path. Oh, actually, I do have this one as available to see. Yeah, all right. So you can see here I've got a new image, Go For Me. This is actually the one that's wrong. So this is actually going to do a path traversal up a directory, but that's actually where the original image is located, so it just overwrites it and it doesn't show anything. But it does actually allow it to push into that upper directory. And so now that we know we can actually do a path traversal and we have the access to the file uploader and it also has a path traversal, what we're going to do is we're going to update my authorized keys file through the API on my system using a local file for my upload. And so now if we do another query of my SSH directory, we can actually see that there's an authorized keys file. And inside that authorized key file is an entry that I just uploaded through an API. So we're path traversing through the API into a safe directory, into a secrets directory on my box, and granting remote access, which then can let anybody SSH into my system. Path traversal is generally due to incorrectly, in this specific example, I have a number of different methods for path traversal in the demo app if you go and actually look through it. One of them is literally accepting a URL path and looking at and literally just straight reading from the OS. The way to go about that in Go is actually there's a number of standard library methods that you can say, I want to launch an HTTP file server, and you pass it the actual path there, and then that actually protects against the path traversals from actually happening. And then there's some stuff in there for actually embedding the static site into the Go binary as well, and that's how you would protect against that in Go specifically. So let's talk about stored and reflected XSS. Let's see what much time. All right. So I don't have any demo for this. Generally, I would have I would have added a UI and stuff if I had some time, but this is generally where uncontrolled JavaScript is being pushed in through the API and then reflected back to the user, or stored in the database and then loaded for a user later on in that same web UI. It can cause things like account takeovers, access to cookies, like session cookies, keylogging users, and a whole lot of other problems. This is not something I'm going to go super in depth to, but a lot of it can be solved by making sure that you're properly encoding the data coming into your API and doing proper data validation. So we talked about all these different vulnerabilities in the app, and it is a function in the app. You guys can go try it out. And then we're going to talk about a few other more higher level, just general application security things. So who's familiar with the difference between encoding and encrypting? Great. The number of people at GopherCon was not quite as extensive. So I'm not going to go too far into this, but essentially encryption is protecting clear text as what's called ciphertext that can only be decrypted into its original form using a shared key or a public-private key. Encoding is actually just changing what the data looks like to look like something else. It's not actually protecting the data in any way. you can encode something as base 64 and decode it as base 64. You don't require any kind of secret to do that. There's two primary forms of encryption: asymmetric encryption and symmetric encryption. Symmetric encryption is like if I gave you a shared password and encrypted a file, you could decrypt it with that same password. Asymmetric encryption is where you can provide, it's a public-private key setup, where you would encrypt the data with your private key and somebody else could verify that it was from you with their, you would encrypt it to their public key, and then they would be able to decrypt it with their private key. And you can verify using information that it came from that person. I have an example of some weak ciphers. This is kind of fun. This is the mascot for Go, if you guys don't know. And this is the Picard Facebook. So there's a form of encryption called electronic codebook encryption. And normally this is shown with a picture of a Linux penguin. But as you can see, it's very well encrypted. You can't tell what the data is in any way, shape, or form. And this is actually a known problem because of how it's actually doing I think it's cipher block chaining, and it's doing it in a sequence of bytes in which, because of how it blocks out the encryption, it can be converted into colors, and you can actually like expose the data. Specifically with this one, it's in an image format called PPM. The speaker notes have all of the cool blog posts where you can actually go and do this yourself if you want. But here's an example of something in RSA 256. So you can tell that the image is very, very different. You can't actually see what the image is. It's properly encrypted, and it's not exposing any data accidentally. Well, until somebody breaks it. So this is the common question you'll hear: what should I encrypt? Disk, transport, or field level? Honestly, the answer is all of them. Some of them come with their own different caveats. Like disk encryption, if you're using something like AWS, Azure, or GCP, like that's only going to protect you if somebody literally goes into the data center and pulls the drive out and walks out with it. And even then, it's probably like, it's probably a part of a RAID, which is then destroyed anyways, or something like that. And then transport encryption, which is TLS. Where data between systems are encrypted, which if you guys know what encoding and encrypting is, you probably know what HTTPS is. And then field level encryption, and this is actually where there's a lot of contention amongst engineers, because field level encryption, while effective against protecting the data if somebody gains access to the database, makes querying data much more difficult, because it encrypts that data with a custom key based on how your user hierarchy is set up, and it's not a straightforward like where clause in a query statement. You have to actually like convert it to encrypted data and then actually compare that data directly, and it removes a lot of functionality you would get out of the normal database. But the fact that it doesn't make it any less valid that field level encryption should be used everywhere. And a good example of that is actually the Equifax breach, where their data was not encrypted at the field level. The disk was encrypted, and then the transport was encrypted, but in the actual database, the field level data was not actually encrypted. And so attackers, when they got that data, were able to actually just extract clear text, social security numbers, and date of birth, and stuff like that. There's a transport encryption handshake. So this is the one that probably everybody here is super familiar with. Who doesn't know what TLS is? Yeah, okay. I'm going to go ahead and just skip forward. Authentication and authorization are who are you and what can you do in a system? There are a lot of best practices. Like OWASP is a great resource for this. And we're actually going to talk about cryptographic hashing with OWASP because there's new recommendations for some of that stuff. Cryptographic hashing is a one-way function, takes clear text and moves it into a form that can't actually go backwards. Proper cryptographic hashing is computationally intensive, and as we get better and better computers or faster computers, it actually causes it to be less effective. And so I actually did a test for the presentation. So I took the SHA-256 hashing algorithm, which used to be one of the best practice recommendations for how to hash passwords, and the new recommendation from OWASP, which is the Argon 2 ID, salted with a minimum of 15 megs of memory, and tested them against each other for the top 1,000 passwords. And what's interesting is that you had your average of the SHA-256 is 1 millisecond per hash to generate a rainbow table. And for Argon 2 ID, it was 27 seconds. Actually, to hash all 1,000 passwords was 1 millisecond. Argon 2 ID took 27 seconds. And so when you're talking about that cryptographic hashing, you want it to be as computationally intensive as possible so that it reduces the likelihood of somebody being able to generate a rainbow table, even if they figured out what the salt was for a hash. Here's a recommendation for best practices. If you're using Go, the Go security team actually does a lot of the stuff in the standard library for you. A good example is TLS 1.3. They will actually ignore every algorithm setting you put in there and automatically choose the most secure algorithms in each release of Go. And we'll update that with different versions. And then we're going to talk about supply chain, because I'm almost out of time, and this is kind of a little more fun for me. So I'm a nerd, and we're going to talk about Git impersonation. And then, everybody here has probably heard of SolarWinds attacks, the CodeCov breaches, left pad and faker, and all these other different libraries and vulnerabilities in different places that essentially cause problems in the supply chain for different security vendors. But one that I nerd out about is the Git impersonation. So let's just go into this. So Linus stopped by to say hi and that he loves kernel con. And this is an actual picture from the project on GitHub with his actual account. You can actually see it here. So I went and did this morning. But because Git in and of itself is not authenticated, it's based off of the user's name and email address that they configure in their Git profile. And so you have websites like GitHub and GitLab and Bitbucket, and this affects all of them. They use that information to tie your account to a specific repository. Now, because of the lack of inherent authentication in a Git repository, you can actually cause something like this. So all I did was wrote a commit with Linus's name and email address, and pushed it up to my Git repository. The reason I'm a nerd about this is because Git does actually hook into signing mechanisms where you can actually sign your code commits. And I sign all of my code commits with a YubiKey. And this is my two commits above this are examples of that. So the one that's marked as unverified is because on GitHub I turned on there's a checkbox that says expect all of my code commits to be signed. And so it's showing an unverified entry there because I purposely bypassed my signing to make that commit. And then the one above that, I actually cryptographically signed it with my private key. And so, there's actually a good deal of potential, supply chain attack that could come in from something like Git, where it's unauthenticated without signatures. And you could start injecting malicious code into an application and actually just impersonate anybody. I could impersonate somebody on my team who doesn't sign their code. You'd have insider threats that are, not even necessarily in engineering. They go in and modify the code base and actually push commits to somebody else. And the only mechanism that I know of right now is the ability to sign those commits individually as the specific author, and then have them verified by the system you're using. So just to recap, we talked about a lot of injections, cryptographic misconfigurations, hashing algorithms, authentication. I didn't go over the third-party library stuff, but vet your third-party libraries. Go through, review their code as if they're your code. They're getting embedded into your binary. Make sure that they're secure. Check their supply chain. Make sure you know what you're actually putting in your application. And be proactive. I said at the beginning, knowledge is key. Knowing what to look for will help you in code reviews to write more secure code. That's it.